Patrick Caldwell, not related to the mayor unless I get pulled over. And then we're definitely cousins. And I work with NOAA, at the same group that has the National Weather Service, but I'm in the branch, National Centers for Environmental Information. We save all the historic records so people can study it for talks like this. And I'm based up at the Department of Oceanography at University of Hawaii, and I've been there since the mid-1980s. And I was originally hired by Dr. Klaus Werke, who's quite famous because in the world of the El Nino, he was one of the fathers of the studies. He came up with a theory on the genesis of El Nino, and so honored to have worked for him. He is now deceased, and but he's quite a legend in the Department of Oceanography. And so let me get to my talk. And so I'm going to give a little bit of background on El Nino and then focus in on mostly about the surf, but I'm also going to show how the El Nino influences the wind. And the question of the day is, what is El Nino and what's La Nina? Sometimes it's hard to tell. It's my daughter from day, whatever, Careers Day or something. And anyhow, El Nino, the term came from Peru because one of the primary influences that the general public first noticed was that when the El Nino conditions set in, it caused the area off Peru, which normally has very nutrient-rich, cool waters, and some of the prime fishing grounds, famous for anchovies in the world. When the El Nino pattern comes around, it's opposite. It's warmer and it's less nutrients, and the fisheries just collapse. So they noticed something was really horrible going on, and it's been that way, word of mouth, for centuries. So they've had that word El Nino, and they use that term because it happens right around Christmas time. So that's where the word El Nino came about. And then at some point later, they had the opposite. When it goes much colder, they just gave it the opposite name, La Nina, for little girl. So little boy and little girl in Spanish. And so exactly how does it come about? Well, it's one of those, is it the chicken come first or the egg come first? It's hard to say, but it's an interaction between the ocean and atmosphere. And with the scientists, we actually have a bigger name than just El Nino. We call it the El Nino Southern Oscillation Phenomena. And the reason the Southern Oscillation Phenomena comes in is that the trade winds are one of the primary ingredients. And because when each scientists need to research over long periods of time to see the repeatability of various cases, and one of the pieces of data that they had available was sea level pressure in Tahiti and sea level pressure in Darwin, Australia. And you can see those records go back all the way into the 1800s. And it just turns out that when you have stronger than normal high pressures near Tahiti and lower pressure there, that's the normal, that's higher here and lower there, but sometimes it gets even further lower here and even stronger there, so you get a really strong amount of trade winds. And then the opposite can happen too. So what you're looking at this time series right here from the 1800s are all these years where you have strong trade winds, and that would actually be La Nina conditions. It piles up the water towards the western side, and then El Ninos when the trades weaken. And so all these were all big, strong El Ninos. And you can see things, in the mainland, with the last several years, we had those La Nina conditions, those big droughts in Texas, etc. Well, they had the famous 1930s, the Dust Bowl. You can see that would have been one of these in here, this big La Nina, where those teleconnections where the weather pattern in the Pacific affects other parts of the world, been going on for quite a long time. And so this is one of, for climate scientists, this is one of the key pieces of information that are used for studying variations in it. This pattern happens to affect around the globe, and I'll talk about that later. So let me go on. So the big point is that this scheme we're looking at right here, just pretend you're in the southern hemisphere looking up towards Hawaii, South America on your right, Australia on your left, and when it's strong trades blow over, that's the basically the normal conditions. So let me move on to the next slide. And so we'll start here with normal conditions. So here we are again with a schematic showing the ocean. And here's the ocean surface with the color code is warm water, where it's redder it's warmer water. And here's South America, and here's Australia. So under normal conditions, you have the trade winds blowing across. And what happens at the equator is that, I don't know how many of you have heard about the Coriolis Force, but it's the motion that makes any kind of movement of air or water in the northern hemisphere go to the right, and in the southern hemisphere go to the left. And so what happens on the equator, when you have it moving along like this, the water goes off to the right and to the left, and it allows cooler water to come up. So you get cool water along the equator. They call it the cold tongue, sort of like being kissed by a turtle. So you have this cold tongue sticks out here. And so you get the water pile up, and then you can go on and get even stronger trade winds, and you get more and more cooling. And then something happens. Suddenly you go into a season and the winds start relaxing across the Pacific here, and this blob starts to move back. And with this blob also comes westerly winds. So instead of trade winds in the tropical band, you start to have westerly winds, and you end up getting a shift of all this warm water across the Pacific back this way. So this is what we're going into now, and I'll show you more pictures, the El Nino conditions. And you can see it's a coupled ocean atmosphere pattern where the wind influences the ocean. The ocean, those winds change the currents, and those currents in turn change where the sea surface temperatures are. And wherever it's warmest, that's your hot plate on the stove. That's where you're going to get the weather, the tropical convection. We know we have Tropical Storm Polly down there to the southwest of us. So, and but the atmospheric pressure is just one of many parameters people use. They use upper level winds, lower level winds, and they have the sophisticated way, what they call multivariate INSO index. That's that El Nino Southern Oscillation. And so anywhere you see red right here, these are El Nino years. And anywhere you see blue, these are La Nina years. And just to point out some I'm going to talk about, this year we are in, it said in the newspaper today, strongest El Nino. It's tied with 1997, 98, and 1982, 83. These are some of the really biggies. In 91, 92, there was also, they categorized it strong. It wasn't quite as strong, but it was also categorized in the strong bracket. So you can see how those change from on the order of the turnaround cycles between 2 to 7 years, roughly, when it swings from La Nina back to El Nino. And this is a good way to look at all the various other strong. This is a diagram for other strongest El Nino events since 1950. And you look down here at the bottom, you see we're actually going to have 2 years. We started December, January. So think 2014. No, this will be 2015. This will be a year ago today, 2015, going into the spring. And here we are right now. And then what's going to happen in the coming year. So one thing to think about with El Nino, if you compare it with the weather, you need to know, are you talking about the year leading into it or the year leading out? So that's one thing to keep in mind. And this is just good to see is how other years responded. For instance, the 97, 98, let's take it, here's the pink. Let's start over here. It sort of like, here's this year, the black ones. It also shot up really sharp during the springtime. And you see 97 was even stronger going into the summer period. And here we are right here. So we still got a ways to go, but you can see the 82, 83 in the green, which is a really big one, it peaked more into the following spring. So if this one is going to be similar, it still hasn't even peaked yet. It could peak now within another couple of months. The Australians today in the newspaper say this already peaked and it's going down, but that's debatable. I'll talk about that a little. And but anyway, that's just a good way to see. And you see, it gets into this pattern. At some point, it falls off like a lead balloon. You know, it just really, really drops down sharp. And for most of these, and but everything in nature, there's always a little bit of variations in everything. Everything's a little bit different. And but the big thing about the El Nino is the surface, ocean surface temperature. And that's the main influence on the weather. And what we're looking at here, this was the global sea surface temperatures from last week. I pulled this when I got into work last Monday. I pulled this down. And you can see Hawaii is right here. So down on the equator, south of Hawaii, is this big warm pool that's on the order of 86 degrees Fahrenheit. So it's quite warm, and our islands here are in the upper 70s. So we're actually still warmer than normal. But anyway, when you have, this is your hot plate on the stove, and where you have your hot plate, you're going to have the weather follows it. That's where you get the convection and rain. But another way we can look at these is see how it varies from the long-term average. So for every point on this grid, you have an annual cycle. The colder winter, warmer summer, wherever it may be. They subtract that out. So this is beyond just what the annual thing does. So this is showing you what is that deviation excluding the annual cycle. And you see it's really warm, on the order of 4 degrees warmer. In Hawaii, you can see, I got a backup. That one just died. Aha. So Hawaii, we're still on the warm side, on the order of 1 or 2 degrees. And I guess I can use this too to move it on. But you can see along the important point is along the equator, this is your classic El Nino signature. And this water moves along, and then it spreads north and south and moves up. So there's still a lot more above normal temperatures going all the way up to Alaska and all the way down to southern Chile that's expected in the coming months, because that water comes across and it's got to go somewhere, and it spreads north and south. And so how does that, when you have that signature of that extra warm water from the center of the Central Pacific over towards South America, what does that do to the weather pattern? And during the El Nino years, what it ends up doing is, they don't have Japan on here, but you can follow Kamchatka down. Japan would be right about over here. Is that the jet stream track, which steers the surface weather features, moves further south, and it's quite straight, comes straight across. But just near to the east side of Hawaii, it splits with one jet going up and over, and then a smaller jet coming right in through southern Cal. And what's interesting is last Monday, I was preparing my talk, so I pulled off. This was the actual jet stream on January 4th. I don't know how many people found this website called Windy TY, Windy T. I don't know, but it's really cool because you can get this globe and then you can zoom in everywhere. But you can look at all the different levels. And on the internet site, all these little arrows are moving. So it's all moving along. But anyway, I went ahead, and this is the upper atmospheric winds. Here's Hawaii. And you can see this path. And I actually went ahead and overlaid. You can see I put the jet stream track, and you can see it coming on, and it's going up and over, and it's going through Southern Cal. And we've seen in the news all week about all the floods in California. So we're doing exactly what the schematic El Nino is supposed to do. So it's always nice when scientists say, hey, I told you so. And so see, it's just pretty much, there's the schematic where it goes up and over. So it's doing exactly what it's supposed to do. And at the surface this past Monday, this is what was going on January 4th. We've had these color codes are the surface wind speeds. So these are getting up gales to storm force winds. And each one of these will be like a little weak low pressure. And the jet stream steers these along. And they move from Japan all the way to California in about 3.5, 4 days. I mean, it's really moving fast. I mean, it goes from the dateline to north of Hawaii in 1 day. I mean, they don't call it jet stream for nothing, and the surface features go with it quite fast. So each one of these weather patterns has those winds rubbing the ocean. That makes waves, and it brings surf to Hawaii. So that's going to be part of my discussion coming up. And the other little things to point out here at the surface is during the El Nino pattern, the jet stream tends to favor one of those loops, they call it upper level trough, east to the southeast of New Zealand, and you tend to get better surf than normal during the El Nino years. And you can see we're doing exactly that. So this was January 4th. So this one was a little weaker. There's several more that came in behind it. So we're expecting a series of out-of-season south swells too, thanks to El Nino. And the other things going on, this is Ula, and this was the politest tropical cyclone I've ever seen. It started over here near America Samoa, went right at it, then moved around it, then was heading right at Tonga, then moved up around it, then aimed at Fiji, then skirted around it, then it got over here and just about to touch it, and then it came back the other way. It was the politest tropical storm. It didn't want to ruin anybody's day. and it's still alive this morning. It's still, Ula is still kicking. It's forecast to slowly move down here. But we have a tropical system, Polly, formed. Here's Hawaii. Here's the date line. Like 3 or 4 days ago, and the waves that are on the south shore today are coming from Tropical Storm Polly. And there's another little low that has now formed at 150 right near the equator. So there's westerly winds. So as I was mentioning, the Australian said that the El Nino's pow, as warm as it's going to be, it's going to drop off. But I kind of disagree with that. When you have all these those westerly winds along the equator from these tropical features, that's one of the main ingredients that makes it warm. It's the easterlies that make it cold, because I mentioned it's not like you have to bring cold air down into the tropics. That never happens. The reason it's cold is because when the winds stress along the equator, the Coriolis makes the water to the northern hemisphere side go right, southern hemisphere side go left. So it spreads, it diverges, and so it gets replaced by cooler waters. That's the reason for all the cool water. When you have the westerly winds, it's the opposite. They call it downwelling. So when you have all that still last week, all this action in the Central Pacific suppressing that, I would think that it's going to make this event, it looks a lot to me, a lot more like the 82, 83 and the 97, 98, where you had a secondary peak in March and April. So we'll see what happens. And here's just a picture of the satellite. This was last Monday. Remember all that warm water south of Hawaii? Well, that's what happens. The percolator is causing all that popcorn convection, and one of those turned into Tropical Cyclone Polly. And in the models right now, we're going into the summer in the southern hemisphere. Yeah, this huge pool of warm water. So it's about the greatest chance you can get to get a cyclone near French Polynesia. And they're actually showing in about 3 or 4 days a cyclone forming that could be in the vicinity of some of the French Polynesian islands. And we may actually get some surf out of it too. The pattern's looking encouraging for surf in Hawaii for in about a week from now, a week to 10 days. And so now I want to shift gears a little bit and talk about the surf. And then I want to be able to show you the long time series of surf records that I have to show you what years were El Nino and what happened during the El Nino years. But in order to tell you the full history, I want to first explain a little bit about surf and about waves, because in general people hear waves, but there's a lot of different words we could use to describe waves. And the basic point is the weather makes the wind, and the wind makes the waves. It's the stress of the wind on the water. And when the wind is pushing the water and building waves, we call that seas. And being a rock in the middle of the giant pond here in Hawaii, any weather pattern, wind pattern, making waves, within 5,000-mile radius can generate those waves. And we don't receive the storm, but the swells move away from the generating zone. And it's basically like you drop a rock in a pond. Those waves that are generated spread out. So as they spread, they slowly get smaller because they're spreading. And also there's some friction. So that you can have 50-foot seas off New Zealand and they end up here around 4 feet. But they do arrive, and when they do arrive as swell, they tend to group themselves into wave period bands, or the distance between each wave of similar length, so they get that real clean appearance. You stand up on the hill and look out, it looks like corduroy lines. That's what the swell is. When you go to Makapu'u and look out, you see all the white caps, all the mumbo jumbo. That's because you're right in the generating zone. It's a strong day of trade. You're right in the generation of the seas. So that's a good one to remember. The seas is a generation, the swells a travel. And then when it feels the bottom and breaks, that's what we call the surf, or a breaker. And if we want to look at the history of measurements about waves in order to describe how El Nino is different from one year to another, we have 2 ways to do it. One would be from a buoy. And what the buoy does is it measures over 20 minutes. And it's surprising you think it'd be the up and down is what it's measuring, but it's not. It's called an accelerometer, that when the waves pass by, it measures this acceleration, and through these mathematical formulas, it can turn it into the numbers that we see. If you pull up the buoy report, it'll give you a significant wave height and wave period, those sort of things. And so one of the information pieces we have are from buoys, and we have them surrounding the Hawaiian Islands. And the advantage of the buoys is you get this high resolution information and lots of various parameters. You know, the wave height, the wave period, which is equivalent to the distance from crest to crest, and the direction from which it's coming. And but there's cons with this data system, because you have this buoy sitting out in the middle of the ocean, and it's getting beaten up by the weather and the waves, and so they break down. And so you can have big, long data gaps. And the other problem is that it's not the surf. What I want to talk about are the actual size of the breakers, Sunset Beach. So that's what you're seeing right here is not the actual surf. So you get a deep water swell, then you can interpolate what the surf would be, but it's not telling you exactly what the surf is. And so then we have to look at what other data sets are available out here. And one of them is visual surf observations. And this is just basically these days, you turn on the radio, you hear Gary Cooley, the Surf News Network, they give a surf report. But back in the 70s, back in the 60s, 50s and 60s, when the surf culture started gaining, various individuals, and these folks live and breathe surf. You know, they watch year after year, swell after swell, these waves building and dropping, and they get a pretty good handle on how to call the numbers. And so this one fellow, Larry Goddard, had been a caretaker for these numbers. He would write down the data every single day, starting in 1968. And he moved off the island in 1987. And that was the year I moved to Hawaii. And I've always been a fanatic too. I'd have my calendar in high school, writing down where I surfed. My surfboards blew off the racks. You know, all the little notes about what I did that day and who I was surfing with. And when I got here, I was so fascinated with the reports of the waves around the island. I started writing it down every day. And we had a couple of months overlap, and our numbers agreed really well. So I met him in the mid-1990s, and we put our data sets together. His were still on paper, had to be digitized. And we digitized it all into the computer. And I still do this every day. So we now are coming up on 49 years of daily surf observations. And so the advantage of that is we're talking about the actual surf, the breakers. It's the surfers standing there at Sunset Beach are looking out, and they call their numbers. And the inherent knowledge base is quite critical, because the waves are breaking so far out there that anyone who doesn't have any experience in the water being out there would have no idea what to call those waves from the shore. But those folks that live and breathe it year after year, and they're out there all the time, they were able to put together their numbers. And like today, after I had my morning surf, I get back, I'm laying in the hammock, drinking my coffee, laptop on my lap, looking at the surf camps. And just right off the bat, I can look at, watch the waves. You get lulls, there's not much happening. But then you see Sunset Beach, it's all closing out. The reef's out there, it's breaking in the channel. Then I'm watching the pipeline cam. You see the third reef breaking, and it's just a mess. It's connecting in. So those are days when they would call it like a 15. That would be the number they would give it, or 18, something like that. So just by those benchmarks of where it's breaking, you can kind of get a feeling for what the size is. And so that's an important part of it, that inherent knowledge base. And the most important, I would say, is it's the longest, most continuous record we have in order to see what is the history of the waves. And then, of course, the cons is going to be, well, subjectivity. Well, anytime you have a human element, there's going to be someone that's going to ask questions. Oh, do they really know what they're talking about? So you have to worry about that. When it's an instrument. Actually, with instruments, you can have problems too. There's technical problems. So I think it goes 50-50 buoys versus surfers on that, because instruments can break down. But they also only have the daylight hours. So how many swells peaked overnight and you missed it during the day? And of course, it's course resolution. It's just a kind of a ballpark number. And then the important point is if you go up to the North Shore and you're looking around, you see so many different breaks, and they're all a little bit different in size. So when you hear the numbers, what exactly do they mean when they talk about, say, the North Shore today, they say 10 to 15, occasional 18. What does that mean? Spatially, where are they talking about? What do they mean by time? Is it always, is it just a nonstop, those numbers, or is there breaks? Or how do you explain it in terms of space and time? And we'll start first with space and spatially. And what this is the seafloor has been modeled into this computer program. And so it knows exactly where these bumps are. Here's Sunset Beach, and the reason it's a surf spot is because the old lava flow and river that came out of here has a deep water, and then you have this reef growth, and so it's like basically a hill on the seafloor. And anywhere there's a hill, when a wave comes out of the deep water, as soon as it feels shallow water, it slows down. So if that deep water's coming in and that hill sticks out into the ocean, right in front of that hill, it slows down. But on either side of it, it's deep. It keeps moving in, so it bends in. And that bending causes the wave to converge, the energy to converge. If you'll notice those waves at sunset have kind of a triangular peak, it's because that deep swell in the channel is moving in towards the shallow part where it's slower. So it's that these hills on the seafloor are what make the surf spots. And this is the 20 meter, 60 foot depth line. So there's a day, 2.5 meters, like 8 feet deep water swell. And this is your typical day. They're right at the high surf advisory, and it's showing the sunset and the pipeline area. Those are the bigger places. And let me move on. And it turns out that these are what we call refractions, where the waves bend in because of the seafloor shape. And these refraction are the surf spots. That's where the reports began and the people congregated, and eventually lifeguard towers were put up. But that's where the surfers started making their reports, was from these places where the waves were biggest. And they wanted them bigger, but they also wanted the fact that it has a channel, so it's safe to get out to the breaks. You can see this one, very distinct channel. So that's one of the critical aspects of surfing, to safely arrive at the takeoff location. And I'll talk about this one later. This is when you get giant surf, and you can see it focuses on the outer reefs. And so that was how spatially what they're talking about. They're talking about the biggest surf spots up there where you have the most bending, most refraction. That's what the numbers mean spatially along the coast. And what does it mean temporally? So for instance, if it's they call it 8 to 12, occasional 15. This is the day where you start to get baby Waimea, a little bit outside the boil on some of the 15s. And what exactly does that mean when they say the waves today are X wide, occasionally Z? So I'm going to try to explain that. And so the big point to remember is that waves are constantly coming in. But for the surfers who sit out here and wait, they want the bigger ones. So according to them, it's just basically flat until a nice big wave comes in. But there's constantly waves rolling by. But they're concentrating on the smaller percent of bigger waves. And so one way to explain this is I wanted to do work with this historic data set and start doing some publishing in science journals. And I had to be able to use the scientific jargon in order to explain what's going on. And so I had to start with the basics of statistics. And if all waves came in, say you had a 30-minute time period and you measure every wave and then sorted them by wave height, this is what you would end up with. And as a comparison, if you say took all the people in this room right here, or say a big auditorium would be a cleaner statistic, it would fall under what's called a normal curve. This is one of your basic things you learn in statistics class, is that once you establish that your phenomena you're trying to study, like the height of people in a big giant auditorium, follows a normal curve, and then as a scientist you go, great, we got all these formulas we can apply, and there's all these standardized methods, so when you write a research paper, you can refer to such and such thing, and then you can speak the lingo of the scientists. So that's what's important. And with waves, it follows, it's not a normal curve, it follows a distribution called a Rayleigh distribution, where you get a lot more smaller ones than you do bigger ones. So that's what the Rayleigh distribution, there's other phenomena in nature that have this as well, but I just want to point out that you see the most frequent wave is much smaller than the significant wave height or the average height. And let me move on. What the surf report was given is that just this little bit right out here, what the oceanographers refer to as the H1/3 is if you took the top 1/3 heights, biggest heights, say there's 100 waves, take the top 33 waves that came through, and then take the average of it, that's your H1/3. So this is what oceanographers use in their discussions. And you have the H1/10, out of 100 waves, take the highest 10 of them, what's the average of those 10? That's the H1/10, and the same with H100. So this is roughly what the surfers were giving, is a smaller percent of bigger waves. And it turns out that for the database that I put together, we always use whatever they call, say today's 4 to 6. That 6 was always the number that went into the database. And Larry did the same thing that I did, because for the surfers, that's the important point. Those are those sets you wait for to catch. And you'll notice when you go by and watch the surf breaks, the guys just sitting out there on their boards for, unlimited amounts of time, waiting for those waves. And in general, it's easy to remember. The H1/10, they come in on average about every 10 minutes apart. The H1/3, they're lower, but they're more frequent. They come in and average about every 3 minutes. The H100, on average, it's right around 100 minutes or every hour and a half. And the H100s, when they say occasional, that's that cleanup set. And the reason they call them cleanup sets is that the surfers never catch them, because a wave will break in water of similar depth. So if the surfers are sitting out there where those normal H1/10s are, and if a bigger wave comes in, it'll be breaking in deeper water, so they get caught. So they call them sneaker sets or cleanup sets, because they get caught by them. And so anyway, we put together this database, so we're now looking at it, and we have from 1968 all the way up to the present. And this is all the data. You can see all the summers down where it's low and the winters where it's big. But the one aspect that made it a little more challenging to describe in a scientific journal is that all the reports have been made in what I refer to as Hawaiian scale or Hawaii scale. And that's been around, that folks have seen in the papers. The people refer to it as the backs of the wave, or there's many other things. And why or when it came about, there's really no clear idea. Somewhere in the 50s going into 60s, it was established. My own speculation is that we had a monster swell in December 1969, and I have a technical report from the Weather Service, and it describes that the deep water swell, it was talking about the days leading up to it, and it was all just typical winter with an 8-foot swell. They'd say an 8-foot swell. And then here comes these really big ones. It's going to be 20 to 30-foot swells when that big one came in. So I think what the surfers used to do is they would get a hold of those weather bulletins, and the weather bulletins say it'd be an 8-foot swell out there, and they go up there and say that, well, okay, we'll call that an 8, because it turns out that when you have a deep water swell around 8, when it feels the bottom, and it actually doubles in size roughly. So when they drop into that peak, what's called a deep water swell 8, it turns into about a 16-foot breaker. It turns out about twice as big. And so I'm speculating that the reason Hawaii scale, which turns out to be about half the size of the actual face of the wave, is because back in the day, the weather surfers would put out the swell, and then the surfers would talk about, hey, the report said eight's coming in. We're going to have an 8. So they go up there, yeah, it was an 8, okay. But I don't know. There's probably 1,001 different people that would have an opinion on how this phenomenon came about, but it's quite fascinating. But as far as I was concerned, I wanted to use this data to study various phenomena, and I wanted to write about it in a peer-reviewed scientific journal. So I had to figure out how to know, is it consistent in time? So what they called 10 back in 1970s, that's still a 10 today. So I did put together a study where I had buoy 1 data, which started in the 1980s, and I compared buoy 1 deep water swelling period with whatever these numbers were. And we don't know exactly what buoy 1 is 275 miles away. We don't know exactly what that was making in heights, but it would make some sort of number when there's a coastal engineering formula where you take the deep water swell and the deep water wave period, you run it through a formula, it gives you a number of what it expects the breakers to be. So all I wanted to know is I have a consistent estimate from a buoy that's independent of the waves. And through the 1980s, I had all the data from the 1980s all the way up into 2000s. We know the buoy stayed the same all the way through, and that formula stayed the same. But if the surfers' way of visually observing the waves changed, when you do a difference on those data sets, there'd be a tilt. And it turns out there was no tilt. And so I published through the Journal of Coastal Research that the Hawaii scale data set has scientific integrity in the sense that it's been consistent. Whatever they called 10 back then is 10 today. And then it's just a matter of translating. So that was my next job, was to translate what does Hawaii scale mean in terms of oceanographically, we refer to the face of the wave. And here's your classic A-frame at Sunset Beach. And because waves have so much, they're dynamic for one, they're constantly changing. And they're different sizes depending on where you are, at the peak, the shoulder, the average. There's a lot of complications that I had to be bold and make a definition of what I'm talking about. So I said, I talk about peak face, that moment of maximum cresting. Whatever that height is, that's what I want to translate to. And so what I did is back in the 2000s, the internet had already come along, and I had all this database on what the Hawaii scale was every day. And I found this website from Claudia Ferrari. She's a professional bodyboarder. She lived up on the North Shore. She was a techie. She'd go out there and take her pictures every day and then post them on her website. This was way before Facebook or MySpace and all that kind of stuff. But she had her own little website, and she posted all these pictures. And it was fascinating in the fact that each picture was the name of the spot and the date. So I could use that data just by the name of the picture. So that just invaluable resource for me. So I downloaded all these pictures, and I tried to find a surfer as a benchmark, say roughly 5 feet in a stance. We don't know which surfer it was. Some are taller, some are shorter. So you get enough of them, it averages out. So it's a real coarse resolution guess, but it's a ballpark guess. And then go into PowerPoint and make a little arrow and then kind of stack up the arrows and get a ballpark estimate. So here was a day that was called 8 Hawaii scale, and I found Claudia's picture, and it's looking somewhere around 15 on the face or so. So it's just what everybody already said. It's about double. So it's always good to tell people what they already know. They feel comfortable that way. But there was so you can see that the primary surf spots when the waves were, at between what they call 1 to 15 Hawaii scale was Sunset Beach and Pipeline in that area. But you get it to a day like today, where suddenly it gets a little bit bigger and Sunset starts to close out. It breaks the channel, breaks further wide. It's just unsafe for the surfers to go there. So historically what they did is when you get the big deep water swells, they moved down to Waimea. And you can see here's the schematic. Here's the 60-foot depth contour. That the waves shift way offshore. It's just way too dangerous. So Waimea was safe in the sense they would be closer to shore. And a surfer, when he gets in the lineup, you're being moved around by the currents, and you get long breaks between breakers. And you need to know exactly where to be when the next breaker comes, to be right where it crests up. So you use triangulation. You sit on the shore, you get a church or a tree, you get a couple points, and then you line them up, and then you get your use that as your navigation to be able to find your place to be. And so the Waimea Bay was the closest break, and it had a bit of a channel. And so that's where all the surfers went. So they knew the numbers quite well when it was 1 to 15. And then once it was beyond what they call a 15, then it's at Waimea, there was no such thing as a 17-foot wave. There was an 18-day, because it's all course resolution, 20, and then they had what's called 25. And that would be when they have the eddy contest. That's a 25-day. And then they have 30 is when, okay, it starts to close out. And then that 1969 one, whoa, it was way beyond closed out, so they call that a 40. It's not that they really could clearly identify how big it was out there, but it was just a ballpark numbering system. So those are the data that started up in 1968 in that daily data set I had. And as I mentioned here, these spots were all zones of high refraction. So they had these numbers associated with zones of high refraction. And when they moved to Waimea, you can see the color codes right off of Waimea. It's not the deep red. The bigger spots, a place called Log Cabins, and there's Outer Pipeline and Phantoms. These are the big wave spots where now in the more recent years, they started to do the tow-in. Back then, no one was towing in. They were just surfing Waimea. But they had these numbers, and it turns out that's why there was so much speculation about, the Hawaii scale. The surfers don't know what they're talking about. Once Waimea starts to break, the scale changes. It's no longer 2. It's actually the scales cross over. And from all the photos I found, it's more like 1.6. So it's true. It's not as big on the face there. But if you look at the same moment, here was a day that they call the breakers at Waimea 20 to 25. So 25 was the regular breakers. At the same moment, out there on that other plot, you saw that deep red on the outer reef where the zone of high refraction was occurring. It was double. And they have the spot over on Maui. When they call 20 Waimea, that's what the surfers give the number for it. And it turns out the wave heights aren't 40 there at Waimea. They're like 32. But at the same moment, on those zones of highest refraction, they are double. And here's all the data. We'll start, here's down on the lower scale, the Hawaii scale numbers, 5 Hawaii scale, turns out to be about 10 on the face. People love to see that, just what they wanted to see. So here was all your numbers from Sunset Beach, and it's basically a 2-to-1. The face is twice the high of Hawaii scale. And here's the numbers for Waimea Bay. They were somewhat less. And but at the same moment, on these same days on outer reefs, it was close to double. So the bottom line is that the surfers created a scale that varies linearly with wave energy, because wave energy is something an oceanographer uses as a term based on what the buoy measures, the deep water swell. It's always, energy is always twice the wave height and the wave period. So it's a formula that I mentioned coastal engineers have. If you got the deep water swell height and buoy period, you can calculate a breaker or estimate a breaker. And that's what we call too is wave energy. But the surfers didn't care about formulas. They were just looking at the ocean every day. But it's interesting that the numbers that they established with this Hawaii scale vary linearly with what an oceanographer would measure from a buoy. So it just goes to show that humans have those that are very intimate with the phenomena they're looking at, like the Hawaiians and their winds and their sailing, is that they can be quite experts in estimating this natural phenomenon. So the surfers get a big pat on the back from the 50s and 60s because they really did put together a data set. So, and this was the second paper I published with the translation to Hawaii scale. And then part of that was where I took the deep water, the Waimea Bay buoy, and I just did a fit on the numbers of the wave height and period to what the surfers called the waves at sunset. And I created a formula. So it's used every day when I go up to the weather service to create the surf forecast, is I used the formula that I created, and it was based on all this data. So there's something nice to be said about having faith, because in the beginning, when everyone was saying, oh, that Hawaii scale, ask 5 people, you get 5 different answers. Oh, that's useless. Forget it. But I proved them all wrong with several papers published in science journals. So finally, after all that talk, we'll just look at what the data are, and we'll very soon get to the El Nino again. This is all the data if you just want to see what's the annual cycle of surf on the North Shore. Here's August, here's January, it gets bigger, here's July. But what I did here is, what's the biggest wave that ever happened on any given calendar day? What's the average that happened on any calendar day? And what's the minimum? Here's the Hawaii scale over here, and here's face, but put into meters. And for instance, here's a very special day, December 4th. It's my wife's birthday. And it's also special because we had the largest event in 1969 that they call a 40 happened on that day. It was this big peak right here. But the average day in right on December 4th is somewhere around 9 Hawaii or 8 Hawaii scale, which is about 16 on the face. But you can get days on December 4th that have been low as like 1 or 2, which is can probably go snorkel at picnic tables. So there's your annual cycle. And finally, back to El Nino. So if we plot all the data year to year, so here we go. We're starting way back in 68. We go all the way up to 2015 or 14. I think it was the last winter. I used it through the winter of 2014-15. And anyway, what you're seeing 3 things here. Here's the year. Here's the count of days per year. So you can see I have 3 different size categories. What we call 8 to 12 Hawaii scale. This is roughly 16 to 24 face. These are big days of sunset. Great, excellent. They had the Triple Crown going. They would be happy campers because that's a perfect big size. And so that's your red. You can see on average you get about 50-something days, 52 or 53 days. And a nice thing to see too is through the years it goes up and down, but there's no crazy long trend. That's another, gives you credence to the data set that it seems to be stable. And so you get, there's your high surf days, 18 to 12. And then when Sunset Beach starts to get a little bit too big and Waimea starts to break, I refer to it in my discussion when I do my surf forecast as a extra large. The outer reefs start to break. But it's not quite the full Waimea yet. We call that extra large, 13 to 19. So here's counts per year that are in that category. You can see the average is around 18, and it varies years to year. And then finally we have the giant category. And this would be days where you're getting close to the ICAL conditions. It would be 40 on the face on the outer reefs. And here you go. On average, it's about 4 days a year. It doesn't happen that often. That's why Quicksilver loves the Eddie ICAL, because they don't have to pay out that contest money. On average, their odds are pretty good. They can keep getting all that free advertising and not have to pay any money for a contest. So their odds are pretty good. The only problem is getting into strong El Niños, the odds go up a little bit. So we'll look here. Here's a 72, 73 strong El Niño. So it was above average in giant, above average in the extra large, and a little bit above average. We go through and look at all these. You see that most of them are a little bit. There was one, 80. Oh, here's 82, 83. Had a whole bunch more of the extra large, not quite as many of the giant. And 91, 92, it had a lot more of the extra large, but fewer of the giant, actually below average on the giant that year. So see, not every year is exactly the same. Mother Nature doesn't like to be easily pinpointed. She's a wily lady and keeps you guessing. And here's a 97, 98. And I had another way to summarize this, is that I counted the seasons where we had above average. That would mean, remember, and this is actually large surf, so anything from 8 Hawaii scale all the way up to giant. So it includes the high surf, the extra large, and the giant. So all those days that would be of concern, that is dangerous out there. And you can see where those years, and for strong El Nino, we only had 4 of them, 72, 73, 82, 83, 91, 92, 97, 98. And then we had this past one. We're in it right now, but I didn't put the plot up there for this year. But we've had 4 strong El Nino events, and every one of them was above average if you look at all the high waves. So that's a pretty good statistic. And you can see as we move from moderate El Ninos all the way to neutral conditions, all the way into La Nina, you see blue and blue and blue. That means less than average. So as you go towards La Nina, the statistics unfold pretty good. So in general, there's a pretty good correlation between El Nino and surf in Hawaii for the North Shore. And here is that one for the giant. And I mentioned that 91, 92 is the only one that was below average for giant surf. But all the others are above. But in general, you tend to have more for El Nino flavor, less for La Nina. And so now I'm going to do the same thing for the South Shore, because the data set started in roughly 72 for Ala Moana Bowls, Larry Goddard's data set, and mine that starts from 87 combined. And this is what your annual cycle looks like. So you see it's much smaller. The other scale went up to 40. This one, mostly the bigger days on average are going to be around what they call 6 Hawaii scale, or about double overhead. So here's the biggest that ever happened on the calendar today. There's a Niki. And this is Cam Day 95 at a monster New Zealand swell. And here's your average, which is roughly around 2 to 3, roughly in the peak months, June, July, August, around 3 Hawaii scale, which is roughly head high. Your head high days at Ala Moana Bowls. So that's what your data look like. And then how does it vary with El Nino? Well, it's not as close of a correlation as the North Shore. But in general, there is I've seen scientific literature that showed east of New Zealand or southeast of New Zealand, the jet stream dust team seem to set up a trough, and that would be a pattern that's favorable for south swells in Hawaii. And but here we just look at some of these. And what's interesting with this, so here's the same thing with 4 to 5, I call a high day, 6 to 7, extra large, 8 giant, just to kind of keep the terminology. But relative to the North Shore, remember our 8 is just marginal. So it's a different ball game on the South Shore. And but just as much emotional, because it's the middle of summer and it's mostly flat and everybody's so excited that there's some waves. So I think the emotions get much higher because people have been denied and they want surf. But anyway, you can see that first off, you see this interesting cycle where we had so many days in the early 70s, and that was a strong El Nino of a high and large. And this year has been one of the most busy south swell years, and it was just nonstop trough southeast of New Zealand. And I've always wondered all the way up till this year, is this data correct? Could that really be true? And some of the people I talked to, like Reed Noyes, told me he graduated from high school in 72. He started his job construction in Waikiki. He lasted like 2 weeks. So the waves are too good. He was looking out at it. He goes, yeah, I remember that summer. It was nonstop the whole summer. That data looks right to me. That's what he said. But I wasn't sure because you had the 90s, we really had some dog years. But finally this year we were been redeemed and we're back to this incredible anomaly. So it can happen when the weather pattern sets up just right. It does what it's supposed to. And so anyway, I'll quickly look at the same thing for the years that were strong El Niños is almost 50-50. So the statistics aren't really too much at your favor, but just a little bit. So you can see the year leading into El Nino, like 72, and this year 2015, we had 3 that were above average and 2 that were below. So it's not as strong a correlation, but there's a little bit of something there. And at least as far as the explanation, there's the trough off of New Zealand. And so finally, how am I doing on time? So do I need to rush through? Am I going over?
You're okay.
Okay, I'll try to speed up going through here. But anyway, we're all aware with the active season. No one here can forget how stressful it was this year with all those different systems going around us with above average systems. And so certainly there's going to be, all for the east side, all of these systems over here produce surf during the summer that was bigger than the trade wind swell. So it was quite a bumper crop. So El Niños tend to be above average in tropical cyclones. And so the chance of east side surf is greater. And here's just a look at looking at other years. The red are the El Nino, blue or La Nina. How many cyclones formed in the Central Pacific? And that's from 140 west over to the date line, basically south of Hawaii. And you see these big years were all El Nino years, but there were some La Nina years that were pretty big, and there were some neutral years that this is a count. This one had 10 cyclones that year, 7 cyclones. So you can see that there is a bit of a correlation. I mean, actually the correlation is pretty good. When it's El Nino, your odds are up that you're going to have more tropical cyclones. And it's the year following, too, so we have to be concerned with the upcoming year, I hate to say. We're not out of the woods yet, but knock on wood. Boy, that was a lot of close calls this year. And so anyway, I'm going to quickly talk about the wind, what the wind does during El Nino patterns. And here's your annual cycle on the wind, and I centered it right over January. And this is just the average of all the various types. This is what I call moderate trades, the red. How many days per month? For instance, here you go into the springtime, you get a lot more fresh trades. Or no, that's actually September. That was September. And then going into winter, the number of trades kind of drop off. But here's Konas and light variables, and this black is behind the front. And so during the winter, you can see a lot more variability. You can get the green Konas, or you can get like today, the light variables. And the blue here is the fresh trades. This is what the kiters want to know about, because the blue means it's enough to go kiting in Kailua. So it's when you get fresher, stronger trades. And it's interesting that you have 3 peaks a year. You have a summertime maximum, and then when you go in right around the Thanksgiving blow, Thanksgiving to marathon, we have a little bit of a bump where they'll get a lot more strong. This year lived right up to it. We had all those good, strong, fresh trades. Then it kind of drops off in January. And this is the average over all years, 1988 to the present. So this is not referring to El Nino. This is just average conditions. And then you get the spring blow. You get a pretty good blow. Then in May, the termites get a hold of the controls, and they make it light and variable because they get hungry, and they want to come into your house. So somehow the termites have gotten control of the wind here, and they made this little minimum. And you even get a little bump of Konas even in May. And there's light and variables. So it's interesting, in May you get that little bit of a bump, but then kicks into summer, and it's back, to more of a steady blow from the trades. But now to look at how this varies with El Nino years. So first is this is the moderates, 13 to 18 miles per hour. And you can see the annual cycle with the minimum over the winter. And here's the average of the 4 strongest El Nino years that I mentioned. And that kind of hovers near the average, but you get a big drop off below average in January. And then that's a little bit below, but not too far off. when you only have 4 cases, your statistics aren't very high. So I would say the only one of statistical significance is this January point. And then here's the fresh to strong trades, and you can see then it also cruises near the average, except for this January, February. So in general, with this data set, I really couldn't say much other than the fact that January and February tend to be an anomaly. And here's Kona and lights, and exactly the opposite, centered right around January. The dashed line are the strong El Nino years. Well, actually, I had the strong and the moderate, so I had more samples. But you can see there's a big peak in the number of days of either light and variable with the yellow or the green. So January really is an anomaly for the wind, and we're experiencing that up there today. We got to check off another in the box of the light and variables for this month. And actually, this data set, I'm going to mention where it came from. This is my data set. I was a keen windsurfer back in the day, and I converted to kiting like all the other people did at one point in time. And so I've been writing down what the wind is, a daily index for the windward side since I moved here. So I have my own little data set that I use. And so that's where this is coming from. And when I'm gone, I use the bellows or whatever other reports I can get to kind of get an estimate. And but anyway, so here's the January for all years, starting in this data set started in '88 roughly, and up to the present. And you can see blue is La Nina years, and that's the fresh trade. So when we have La Nina, the kite surfers in Kailua are really happy because you get way more days of, some of them 20 days of fresh trades. But when you go into El Nino like this year, it's the opposite. See, the fresh trades drop way down on the El Nino years, and you get a lot more Kona days or light and variable. So as far as the influence of El Nino, yes, there is a strong influence on January wind in Hawaii. Other months, it's kind of 50-50. Some are above, some are below. And so we're looking at the forecast, what's coming up. This is the latest from the Forecast Center for a present strong El Nino. And see that they're all showing it dropping down. These are all models, all these different color codes, different groups that model, NASA and all kinds of places. And so in general, all of them are showing it's supposed to tick down, but some of them are kind of keeping at least, actually some of them do show a peak into the spring, and that would be my gut feeling, that it would continue February into March and then drop off real sharp. And because here looking at these are all the ones, here's the 97, 98, it kind of kept going into March. In 82, 83, it had that secondary peak. So I'm kind of thinking we're going to be doing the same. And for that year, 98, we had, for the fresh trade winds that the Kailua kiters want, we had below average in March. It was really slow. It was almost like January. But then in April, it went above average. So it was a real sharp transition coming out of that 97, 98 to suddenly bingo. And then that's usually what happens when you leave the El Nino. It falls into a La Nina pattern. And so, and it's quite a sharp transition. And then the local response is immediate. You get the above average. And then you can see that back in 92, this black line right here, it did not peak until March. So it's kind of an odd one, this 91, 92. Most of them peaked back here in December, January. This one was late, but it was interesting. But that one that peaked here, we had a real low below average number of fresh trades. So here's a correlation between that maximum signal and the trades here. So as far as kiters are concerned, February and March are still probably pretty slow, but by April it should kick in. That would be, I would take from this bit. And then there's another one of the official forecasts. These are all El Nino. What's the probability of El Ninos? 100%. November, December, January, December, January, February, March, April. So they're keeping the stat above 80% all the way March, April, May. So that was kind of what I'm thinking too, seeing those westerlies still on the equator right now with those tropical storm Polly and all, that it's going to be a while. It's not going away anytime soon. So we'll have influence on the local wind and surf. Will be above average surf into the spring. But then it should drop off, and they say they're bringing in La Nina towards going into the summer. And the last big question is is there any correlation between global climate change and El Niños? And well, let's just look and see what the data says. These are the global temperatures from each month since 1982. And any month that was a El Nino flavor, it gets colored red. And any month that was a La Nina gets colored blue. And these are the neutral ones, the gray. And so you can see as time went on, these El Nino phenomena, you can see that all the El Ninos in general, the global temperature, it influences the entire globe. When the El Nino occurs, the entire globe feels it. And so the global temperature is warmer than normal. You can see this up and down with the El Nino year. So it's quite the influence. But what's happening is you can see they're getting stronger. So the trend is getting greater. So that influence is going to get greater. And what that means for the future means that the computer modelers will have a lot of work to do, because whatever they tried to model back in the 80s will be different, because that expansive warmth, what they're talking about is a different magnitude and a different coverage. So it's going to keep the meteorologists and oceanographers well employed way into the future, trying to figure all this out and estimate what it is. But there's certainly a trend in the data upward, and the El Ninos are getting stronger. So that's takes me to the end for my questions. Yes?
We went to North Shore Monday to
okay.
see the waves. And you answered a question we had. Where do they measure it? The back side or the front side? So it's the face that they measure the height.
Well, it's the whole long-term Hawaii surfers don't use either. As I mentioned, it's like a benchmark. When it gets big like that, they look out there. It's a look and feel of the ocean, where it's breaking along the reef. So it's really neither in terms of the long-term surfers. And so back in the day, if they would have never put the word feet at the end of it, they would have said today is 5 feet up there, and really on the face it was 10. Everything would have been okay. They would just say it's a 5 up there today. And then it'd be like a river rapid, a dimensionless number that represents the rise and fall. But the problem with the system was that they didn't use the word feet. They said today's 5 feet, when it really wasn't 5 feet. And what did that 5 feet mean? It meant nothing, because it was so hard to interpret what it was. That's why I went through that whole process to translate it. So the best you can do is ask somebody, what's the peak face? I always try to tell people that want to talk about the face, because as I mentioned, the wave is dynamically changing. It comes in, it crests up, it breaks, and it's changing, constantly changing in height, and anywhere along the wavefront can be a different height. So it makes it, you have to be very specific in your definition if you want to talk about the face of the wave. So that's why I try to use peak face. But I still like the Hawaii scale in the sense it's been consistent. And as I mentioned, when you can use those inherent benchmarks for estimating the size, like I can lay in my hammock and look at the cams at Pipeline and Sunset and Waimea and go instantly, okay, that's roughly 15 plus or minus a few in Hawaii scale. So it's the benchmarks are important.
So when the lifeguard, we asked the lifeguards what they think, and they said we're seeing between 20 to 30 feet.
Oh, okay,
so
that's good.
That's pretty reliable.
The
lifeguards, that'd be the.
Yeah. I mean, the lifeguards, that's their job, is to try to keep you safe, and it would make sense for them to underestimate it. And they do underestimate it when they send it into the general report. They'll use Hawaii scale all the time because that's what they're comfortable with. But if they're talking to someone on the beach, they know that person's, may not, you're not wearing your surfer wear stuff, surfer dude. They're going to explain to you the best they can in a layman term to translate it into a peak face.
Thank you.
Yes.
The previous slide where you showed global temperature, is
Yes.
that a water temperature or an air temperature?
That was air temperatures. Those are global air temperatures.
So when we hear things or read things and they're talking about global temperature, is it generally an air temperature that they're reading?
Yes, but they can go either way.
Yeah.
That would be the default, would be air.
Okay.
Surface air temperature.
Okay.
Where but there is a lot of products that use global water temperature, which would be this And that you have to be careful too, is it the surface or which depth?
How deep?
But in general, the default, when they just say temperature, would be the surface air temperature from all the airports.
Great, thank you.
Yes?
You had mentioned a website, you got those neat.
Oh, yeah, it's called Windy, W-I-N-D-Y, Windy, and then the letters T-Y after it, windyt.com. And it's an excellent website that you can, along the bottom of it, you can click on it to get forecasts. It has a radio buttons. You can get temperatures, winds, pressures, clouds. Really excellent, modern website that's free. I really love looking at it. I'll get it, and it starts out with the whole globe, but you can zoom in if you want all the way down to, look at Kailua. You can zoom in pretty well. So it's got a really nice zoom, and then you can rotate the globe anywhere. And so that's a lot of fun, that website. Windy T, I guess. It's kind of an odd name, but that TY must be something. I don't know.
Well, thank you so much.
You're welcome.